Hello, this presentation will cover two-factor ANOVA with Kij equals 1. The definition of two-factor ANOVA with Kij equals 1 stems from the fact that there's two factors now in the analysis of variance, and each factor, A, having associated levels I and B associated levels J, have one observation across each level of their factor. So as you see, x11 will be associated with factor B at level 1 and factor A at level 1. This ANOVA follows a fixed effects model, which basically states that there will be an effect seen on the true average response when factor A is at level I and factor B is at level J. The additivity model is an extension of the fixed effects model, which actually defines that relationship, as said in the previous slide, between the differences in mean responses across levels of one of the factors with the differences observed in all levels of the other factor. So by using the additivity model, you can guess that it will be easier to see variances associated with each factor at each level in the ANOVA analysis. If you look on the left, there's a graph that shows an ANOVA experiment that has a pretty noticeable additive factor, while factor B, while the graph on the right does not. The calculations in two-factor ANOVA with Kij equals 1 is very similar to that of single-factor ANOVA. The only difference is that you now have an individual sum of squares for factor A and factor B, along with estimated mean square values with A and B. The fundamental identity represents the added factor also, where you see that SST equals SSA plus SSB plus SSE. Hypothesis testing is similar to that of single-factor ANOVA, except again, there's two factors to consider. Factor A across its I levels and factor B across its J levels. And the test statistic represents that difference. This is an example of a sample two-factor ANOVA table with Kij equals 1. As you see, it's taken into account factor A and factor B. Two-factor ANOVA has correlations to engineering that can be seen in basically any engineering experiment you'd want to conduct. It can be seen in materials tests to see factors associated with stress, strain, and strength on a material, in design specifications, which factors involving best methods to use in design, and then also treatments to certain materials. So you can see which treatment to a material affects the true response of that material based off another factor, and so on.